So it's not only carbon that can form hybrid orbitals. Nitrogen and oxygen and a lot of other elements, sulfur and phosphorus and things like that, can also hybridize. So let's just deal with nitrogen and oxygen right now. So nitrogen, in its bonding pattern, if it's going to be neutral, it normally has one lone pair of electrons, so that its 5 valence electrons will make 3 bonds. Why is that? Well, let's draw nitrogen with 1, 2, 3, 4, 5. For it to have its octet, it would have to pair with 3 hydrogens, for instance. So it makes 3 single bonds. It needs to bring in 3 more electrons in order to get up to 8. So 2 of those electrons, though, just remain on nitrogen and aren't involved at all in the bonding. So take a look at methylamine right here. The bond angles are roughly tetrahedral. So 107, 110 are roughly similar to that 109.5 tetrahedral bond angle. The hybridization is sp3. 3 bonds are single bonds. It's sp3 hybridized, just like carbon. You can tell by the geometry. It's that tetrahedral geometry. So sp3, sp3, sp3. The 4th hybrid orbital will be occupied by the lone pair, the non-bonding electrons. So just like we saw in oxygen before, in formaldehyde, the lone pairs can occupy a hybrid orbital. So I've got a model of methylamine. So we can tell that it's sp3 hybridized. We see those 4 sp hybrid orbitals on the nitrogen and 4 sp hybrid orbitals on the carbon. The difference between nitrogen and carbon is it has 1 more electron of its own. So rather than needing to form a bond on its 4th one, it already has a pair of electrons just there. So that's in yellow there, that's where that lone pair of electrons is. It occupies the same type of space that a bond would normally occupy. So that's going to be important for learning shapes as we continue on here, that a pair of electrons takes up just as much space as a bond does, and that's because they occupy a hybrid orbital, just like these sigma bonds do. So the carbon is tetrahedral. Let's go back to my page here. The carbon is tetrahedral. Has 109.5 bond angles, has 4 bonds, so it makes a perfect tetrahedron. The nitrogen, with its lone pairs, the electrons are sort of in a tetrahedral arrangement, but the shape of this nitrogen itself is called trigonal pyramidal. Notice the electrons occupy the spaces around the atom, but when we talk about a shape of an atom, we're only counting the bonds. So we're only counting the places where that atom is connected to other bonds. So rather than calling this a tetrahedron, that lone pair takes up space, but we don't really see it when we're saying the shape. So just looking at those bonds, this nitrogen looks like a pyramid. Go back to my 3D model here. I'll take the hybrid orbitals away. Let's leave the lone pair there, though. The nitrogen, you can see it just like that. It looks like a pyramid if we count those bonds. The lone pair of electrons is what's pushing those bonds down out of the plane. So something similar can happen to oxygen. We saw oxygen's hybrid orbitals in formaldehyde before. Here's an oxygen that's making single bonds, which means it's sp3 hybridized again. So oxygen will make 2 single bonds and have 2 lone pairs. So the shape around the oxygen, it'll seem tetrahedral because it has those 4 of those sp3 hybrid orbitals. But it turns out lone pairs will occupy 2 of the sp3 hybrid orbitals. So the remaining shape around that oxygen is called bent. You saw that in your activity. Remember, electrons take up space. Lone pairs take up just as much space as a bond would, but when we're talking about the shape of something, we only count where the bonds themselves are.